And welcome to the London Machine Learning Meetup. I'm Giuseppe from Evolution AI, and we'll have the pleasure to introduce Ofir Press from the University of Washington and Artem Solos from Mila in Montreal. So Ofir is going to talk to us about the complementary scale, novel guidance methods for improving language models, and Artem is going to moderate the talk. So a few announcements before we start. So as usual, you can ask questions using the Q&A tool. Ofir said please ask questions during the talk, especially if you have doubts about the material that is being covered, so that we can answer them during the talk. If you have any technical issues or any other questions, you can ask them to me via the chat. As usual, the talk is going to be recorded and will be available on our YouTube channel. So don't forget to follow us. And one last announcement is keep an eye on your emails because there are going to be some in-person events shortly. So yeah, stay tuned for the latest updates. So I leave the stage to Ofir for the talk.
Thank you so much for having me. Thanks everybody for coming. This talk has a complicated name, but it's going to be very simple. I'm just going to talk about a few papers that I wrote during my PhD. I'm going to start by talking about ALiBi and Shortformer, and I'll just briefly talk about them. And then we're going to talk about something completely different, this prompting paper that we wrote called SelfAsk. So if you lose track of what's happening in the first 10 or 15 minutes when I talk about ALiBi, don't worry, because when we talk about SelfAsk, we're starting from scratch, so you can rejoin then. And yeah, you can if you have questions, we can do questions during the talk. Okay. So for the purpose of this talk, I'm going to define a language system to be any computer program that has some natural language component. And so like Siri, Google Search, Translate, ChatGPT are all language systems. And at this point, it's very critical to everybody. It's very obvious to everybody. The language models are critical to language systems. All of these programs that I showed you are either just a language model or something just on top of a language model. And even things that in the past were not language models, like a translation system, we're now discovering that language models can actually translate better than translation models. And so improving language models is obviously super important. And one kind of approach is to say that if we increase the size of a language model, they're going to improve upon many metrics. So a proposal for solving NLP would be to just increase the size of these models. And it's not something that's always easy to do. It's a lot of engineering work. And it does, indeed, increasing size does, improve the quality of the language model that you have. But over the last 5 years, I've shown that a lot of properties of language models actually don't improve with scale. And so I think that working on larger language models is great, but we can't just do that. We also have to think about new architectures, new sampling methods, new algorithms for making better. We can't just make them bigger. We also have to make them smarter. And so, yeah, over the past 7 years, I've shown a lot of different methods that improve language models without scaling them up. And today, as I said, I'll talk about ALiBi and Shortformer, and then I'll talk about SelfAsk, and then we might have some time to talk about future work. Okay, so let's talk about ALiBi. But before we talk about ALiBi, I'm going to talk about this long word, extrapolation. So when we train language models, we have this big corpus of text that we crawl from the internet. And what we're doing is we're feeding in, we have all these documents, and we're feeding in the first word, and we're asking the language model, hey, what do you think the second word is? And then we're getting some loss from that, and then we're feeding in the first 2 words of a document and asking it what the third word is, and then the fourth word and asking what the fifth word is, and so on and so forth. But we train language models on GPUs, and GPUs have a limited capacity, right? They don't have infinite memory. And so what ends up happening is, even if we have a document of, say, 50,000 or 100,000 or even, I don't know, 30,000 words, we can't fit it all into GPU memory at once. So if we have a document of length 50,000, at some point, right, we'll try to predict the 1,000 word, the 2,000th word, and so on. At some point, we're going to run out of memory. We will not be able to feed in 50,000 or 100,000 words into memory. And so we're going to have to take that document and chunk it up into smaller segments that we can fit into memory. And so when we train, we have something called the train length, right? So I think LLaMA 1 was trained on 2,000 or 4,000 tokens. I think GPT-4 is trained on 8,000 tokens. They all have a limited training length. And they can't really consume sequences that are larger than that training length, which is really annoying, because you might, be building like a programming assistant, and you have a code file that's larger than 8,000 tokens, and you want to use GPT-4. You can't do that. Or you want to write a book that's 100,000 tokens, and you want to write a book that's 200,000 tokens, and you want to use Claude. Well, you're out of luck, because Claude only can take in 100,000 tokens, right? So extrapolation is the ability of a model to either read or produce sequences that are longer than the ones that it was trained on. And because GPUs are limited, because we're only going to be able to train on limited text sequences, but at inference time, we're always going to have larger code bases that we want to do code prediction for, larger books we want to write, larger legal documents we want to process. Because of that, extrapolation is a super important topic in NLP right now. And if we go back into the original transformer paper, Vaswani 2017, they wrote that the transformer that they proposed may extrapolate to sequence lengths longer than the ones encountered during training. So they already said that they thought that their original transformer model could do that. And so when we wrote ALiBi 2 years ago, the first question that we asked was, can existing models actually do it? And so what we did was, we took just a normal transformer language model, and we trained it on 1,024 tokens. And then we evaluated it on 1,024 tokens. So we're evaluating using perplexity, so lower is better. And this is like the typical thing to do. You train on 1,000, you do inference on 1,000, and we got like 18 perplexity, which was okay for the time. But then we did something that for some reason nobody had done up to that point in a paper. We were like, okay, so you can obviously understand 1,024 tokens, but what happens if I feed you 1,025 or 1,026 or 16,000 tokens? Can you understand that? And perplexity went way up, which is bad, right? Higher perplexity is better. So we're giving the model a longer input. We're giving it more context, but it's giving us worse results. That's kind of like if I gave you chapter 9 of a book and asked you to predict words from chapter 10, and then I gave you chapters 1 through 9 and asked you to predict words from chapter 10. If I gave you chapters 1 through 9, your predictions should be at the same level, the same accuracy level, if those chapters, those more previous chapters were not relevant, or your predictions should be better if those previous chapters were relevant. What definitely should happen is that your predictions should not get worse, which is what we see here. So the normal transformer model cannot extrapolate. Now, just to explain this sinusoidal label here, the normal transformer model was proposed with 2 different position embedding systems. One is called absolute position embeddings. One is called sinusoidal. The absolute position embeddings, they can't even theoretically extrapolate. They would give you a runtime exception. So that definitely won't work. Sinusoidal models, when they were the sinusoidal position embedding method, when that was proposed, they said that it might be able to extrapolate because theoretically it could extrapolate. But what we showed is that in practice, it does not extrapolate. So yeah, the normal transformer language models cannot extrapolate. And then we just went in and we took out the sinusoidal position embeddings and we put in the rotary position embeddings. which are not very popular, but used in LLaMA. If you don't know what rotary position embeddings are, it's basically instead of adding position representations to word vectors at the bottom of the transformer layer, you dot product the position embeddings by the word embeddings. And you do it only to the keys and queries, not to values. It's a slight modification of the sinusoidal position embedding method with a lot of math behind it that isn't really required to understand what's going on in there. But yeah, that also doesn't really extrapolate at all. Again, performance gets worse as we give it more context, which is not something we want to see. And then we tried something called the T5 bias, which is the position embedding method from the T5 model. That's very popular. And that kind of could extrapolate. And so when we saw that, we were like, okay, it seems like extrapolation can be enabled by simply swapping the position method. The transformer model is a really big, complicated machine, and we didn't know what parts we'd have to tinker with in order to get extrapolation to work. But it seems to be, extrapolation seems to be an issue that is mainly dependent on the position embedding method. And so, yeah, we came up with this new position embedding method that's inspired by T5, but it's faster and simpler, more elegant, and it works much better. It's called ALiBi, and now we're going to talk about it. And yeah, it works better than everything else, and it's also faster. So ALiBi just encodes a bias that all of us as humans understand, right? When we're reading a piece of text, we know that the closer a word is to the current word that I'm reading, the more relevant it is, right? And this is a dynamic thing. As I read, as I go more to the right, the words that are more to the left become less and less important. And position embeddings kind of try to tell them all, hey, this is word number 1, this is word number 2, this is word number 3. But what we discovered during the course of our research is that transformer models overfit to position representations. So instead of kind of understanding, okay, this is position 9, that's position 7, and I'm 2 words away, instead of doing that kind of relative understanding, they overfit to specific position embeddings. And so if you give them a position embedding they've never seen before, like you train it on 1 to 1024, and then you give it position embedding 1025, it just explodes. It's like, wait, 1025? I've never seen that. What is that? It doesn't understand that 1025 is just 1 away from 1024. And so the way to solve this is to, in my opinion, not use position embeddings and instead do this relative attention thing that we do with ALiBi. So yeah, the first thing is we comment out position embeddings. So there's no position embeddings in this method. And then the second thing that we do is we add a bias to our attention scores that provides us guidance to do what humans do automatically. The further away a word is, the less I want to look at it. So here's how we're going to do it. So I have this sentence, the quick brown fox jumped over the lazy dog, and we're now trying to predict, sorry, it's all the way to over. Over is the last word. We're trying to predict the next word. So the word over is a query, and we're tending to all the keys. And so usually you just dot product these 2 representations, and those are your attention values when you're trying to predict the next word. But what we do with ALiBi is we just subtract the distance between the key and the query, right? Again, so the sentence is the quick brown fox jumped over, and we're trying to predict the next word. So the current word is over. So the distance between over as a query and over as a key is 0. Distance between over and jumped is 1. Distance between over and fox is 2, right? And so we're just telling the model, hey, compute attention as you normally do. But then the further away 2 words are, the more further they are, the more distant they are, the more I'll penalize that score. That's it. That's basically ALiBi. Just that if you do exactly this, it won't really converge during training. So we multiplied it by this constant factor m. It's not learned. It's just a sequence of values that we discovered. And it's different per head. So if you have 8 heads, you use these m values. If you have 16 heads, you use these values. For n heads, you just have this formula for coming up to these m values. And yeah, that's ALiBi. It's used by lots of models, by Mosaic ML, Replit, Big Science. Yeah, are there any questions about ALiBi before I continue?
Can I ask a question?
Can you ask a question? Of course, yeah.
Yeah, so I'm wondering, like you improved like like the ability to like keep perplexity the same, but I'm wondering, like, did you also accidentally improve any other metrics like unbiasedness, like faithfulness, usefulness, and so on? Because
Yeah, go ahead.
yeah, because I've seen a couple of methods that like manipulate that are trying to like improve those metrics, and they basically manipulate with like attention rates.
When we originally put this paper out, we only evaluated these models using perplexity. Big Science had more evaluations of ALiBi against other position embeddings methods, but their ALiBi just improved across the board. So I don't really know to speak
Okay,
to any like specific downstream effects on specific topics.
Okay, I see.
Any other
Thanks.
questions? Let me read these. You looked into how the assumption of ALiBi regarding the importance of yeah, we haven't quite done a study of how ALiBi affects different languages, but you're totally right that different languages have different ways in which different distance affects them. But the overall concept here is that the further away a word is from the current word, the less it matters. And I think that that's pretty much universal. But yeah, I don't have anything more specific on that. Oh, somebody's asking what the first step was. The first step was just, it's not really a step, it's just to comment out the position embeddings, because we do not use position embeddings in ALiBi. Final question? Okay. So now I'm going to talk about another paper I wrote called Shortformer. And it's actually becoming super important right now because now there's lots of different models. So I wrote these slides a few weeks ago, but now they've kind of become somewhat deprecated because LLaMA 2 is out. But you'll still get the idea here. So we have lots of models now, right? When LLaMA came out, it was a model that was trained on 2000 and does inference on 2000 tokens. But then somebody discovered this trick, right? Where you could take the normal LLaMA model, you're not doing any fine tuning or extra training on it. And then you can use it to do inference on 4,000 tokens. And then somebody found a different interpolation trick where you could do inference on 8,000 tokens. And then Mosaic had this totally different model, which they trained on 2,000, but then they did further training on 65,000 tokens, something that we call stage training. And then they do inference on 65,000 tokens. And so you have all these different models, and you want to compare them, of course, and you want to know which one is best for your use case. And so one thing that people do is they just kind of compute perplexity on a depth set with a bunch of these different models, right? So this is a tweet I found, and it doesn't really matter who wrote this, but they compared LLaMA 7B with like the normal LLaMA 7B to LLaMA 7B with the interpolation trick, and they got a lower perplexity with the LLaMA with the interpolation trick, and so they were like, oh, this is so much better. So lower perplexity is better, but this way of comparison is actually incorrect. And let me show you why. So you can't do this comparison because of something that in the Shortformer paper we called the early token curse. And here's what it is. So you have these two LLaMA models, right? One of them processes 2,000 tokens and the other one processes 4,000 tokens. And you're computing perplexity over a development set. So what's a development set? Somebody mined a bunch of documents and they just concatenated them. So let's say it's 1 million or 100 million tokens that you're going to use as validation. So hopefully you didn't train on them. And obviously your model cannot read in 10 million tokens at once. So you're going to have to segment these 10 million tokens, right? So when you do this for the LLaMA, the original LLaMA model, it's going to look like this. And when you do this for the LLaMA model with the interpolation trick, it's going to look like this, right? There's going to be half as many segments because our segments are twice as long. And then you're going to compute perplexity for this segment here, and then this segment, and then this segment, and that segment, and that's going to be, you're going to average those. That's going to be your perplexity for the original LLaMA model. And then with the modified LLaMA model, again, you're going to compute the perplexity for the first segment, the second segment, and so on, and then average them. That's going to be your perplexity for the second LLaMA model. But this comparison is flawed because of the early token curse. If you look at the predictions your model makes, you will see, and you should run this because it's really cool to see, that the first 5 tokens are the hardest to predict by far. The first token is the hardest to predict because you're trying to predict a token with 0 context. And so you're going to be super wrong. And the second token, you're trying to predict the token with 1 word of context, you're going to be very wrong. And so when computing complexity, most of your loss mass comes from these first 5 tokens. And so it's unfair to compare the original LLaMA model to the interpolated LLaMA model, because the interpolated LLaMA model, the one that handles 4,000 tokens, has half as many early token curses to deal with. So you are giving it a much easier challenge to complete. And so it is expected that it will do better. And just because it does better doesn't mean that it's actually a better model. So one solution for this is to use sliding window evaluation. So this is a diagram I made for one of the papers, but at the bottom, you see the evaluation that I just showed you before. I call this non-overlapping evaluation, where we have these segments that are totally independent of each other, and we evaluate the first one, and the second one, and the third one, and so on, and then average those. So that's on the bottom here, right? We have a example sentence that has 8 words, and we have an example language model that can only handle 4 words at once. So if we do non-overlapping evaluation, we evaluate these 4 words first, then these 4 words. And that's what people typically do. But if you want to compare models of different lengths, you should use sliding window evaluation, which is shown here in the blue diagram on top. And what we do in sliding window evaluation is our first evaluation is the same as before. We just evaluate the first 4 words, but then we slide our language model 1 word to the right, and we just evaluate the word sat. And then we slide it 1 word to the right again, and we just evaluate the word on. And so every time we're actually making a prediction about just the last word. And so we don't have this early token issue anymore. And that equalizes the playing field between models of different lengths. And so let me show you some numbers. So this is from our short form paper from 3 years ago, but these concepts are still very important. So what we did back then was I trained 8 different language models on different training lengths. And then I ran the validation perplexities for these models using non-overlapping evaluation. So this is non-overlapping evaluation, the baseline thing, the typical thing that people do. And what we saw was that these models seem to get better the longer I trained them on. So the perplexity for the model trained on 3,000 tokens was the best. But then I ran the sliding window evaluation. And what we saw here is that at first, it is better to train on longer sequences. But then when we get to 1,000 tokens, we actually stay flat. So the perplexity for 1,000 and 3,000 here were the same. And so while at first it looked like training on longer led to bigger models, we discovered that this advantage that kind of seemed like an advantage here was actually the models just having less of an early token curse to deal with, and that's why they were getting better performance. It wasn't because they were actually better language modelers, and the sliding window evaluation showed that. So this is super important today too. Longer models aren't always better. It's very important to know that. And if you want to compare models of different lengths, one way to do that is to use sliding window evaluation. Do not use non-overlapping perplexity numbers, as I've seen a lot of people do on Twitter, because it's just incorrect. And you're going to get results that will mislead you. Yeah. So, so sliding window is an evaluation method that's much harder to run. As it's much less efficient, but it gives you a much better view of what your model is doing. And when we did this for ALiBi, we discovered, so we first did this for a sliding solo model that was trained on 512, and it just explodes if you use sliding window evaluation. But ALiBi, also trained on 512, leads to a flat line. So what we're doing here is we're taking a model that was trained on 512 tokens with ALiBi, and then we're giving it 1,024 tokens, and we're evaluating it on that, but we're using sliding window evaluation. So this is the more accurate way to evaluate. And this time we're seeing that ALiBi is not able to extrapolate to longer sequence lengths. So while ALiBi is much better than everything that came before it, those methods all like totally explode when you give them longer inputs using sliding window evaluation. It still is not able to effectively consume sequences that are longer than those it was trained on. I have more about this on my website. It's a really long topic, but basically even with all these tricks that we're seeing, the LLaMA extrapolation trick, different position embedding methods, it's kind of impossible right now to extrapolate. If you want to understand n tokens during inference time, you have to either train or fine-tune on n tokens. Otherwise, you will not understand n tokens during inference time. So for example, there's this new LLaMA 2 code model that can understand 100,000 tokens, but it can do that because for a bunch of time at the end of training, they trained it on 100,000 token long sequences. So that's the current state of the extrapolation world right now. And just before we move on, there are a few other good ways to evaluate models of different sequence lengths. So what we've said until now is do not use non-overlapping evaluation, the typical baseline method, because that's a bad way to compare models of different lengths. Do use sliding window evaluation, but also here's a few other things you can use. So just check it on downstream tasks. If you're a company that's building, I don't know, a summarization tool, or a researcher that's working on summarization, just take your two different models and just test their accuracy on a summarization data set. If you're building a legal aid, test your two different models on a legal benchmark. The early token curse is not going to be valid over there. And so, yeah, that's one thing you can do. And then I give this example of this company put out this thing called OpenChat. And they have two different models. One is 2,000, one is 8,000. And they don't show any perplexity numbers, which is okay. They do this downstream evaluation with Vicuna GPT-4. And I think that's a great way to evaluate different models. And then the last thing I'll talk about is these plots, which we're seeing pop around now. These plots are great. They're also a great way to see how your model, these are great to compare different models that handle different input lengths. So what this plot shows is perplexity averaged over every individual input location. So this gray line here is the original LLaMA model that was trained on 2,000 tokens. And what we can see is near zero. So in the first few tokens, when you compute perplexity, as I said, it's really, really bad, right? Because you're trying to predict words with very little context. So it's getting horrible perplexity. And then as you give it more context, it gets better and better and better and better and better. Up until at 2,000, it does really well. And then, as I said before, existing models cannot extrapolate to longer sequences. And so as soon as you pass 2,000, sometimes it can extrapolate for like 10 or 100 tokens beyond 2,000. But as soon as you pass 2,100, it can't extrapolate. And so perplexity just explodes and it returns really bad predictions. And then they had this kind of scaling method, the scaling trick, and it is able to handle sequences that are longer, but it's doing it worse than this gray line was at 2,000. So you have a model that can handle longer sequences, but at a much worse, this line is much higher than the gray line. And so there's no real reason to use it. You could just use this gray thing and just slide it over. But that's too deep for this talk. Yeah, if you want to learn more about this, there's a blog post on my website, ofir.io, and it's about relative positioning, and it talks a lot more about this stuff, and that's a great resource. Any questions here? Because this is the end of the ALiBi and evaluation section, and then we're gonna go talk about prompting. And I see we have an ALiBi question, so I'll answer that first. And you guys, if you have new questions, you can ask me. So Laura asks, where does the formula used by ALiBi come from? We invented it in the ALiBi paper. It's inspired by the T5 position embedding method. It's inspired by the synthesizer transformer. But yeah, it was something that we came up with for the ALiBi paper.
I'll ask a quick question.
Yes, go ahead.
So I understand that these words that I'm going to mention, they came quite like a bit later than yours. But still, I'm wondering, like, there is a huge direction about like extrapolating the context sense in training and in inference of transformer. Like, by like a lot of orders of magnitude, like long nets, quantized transformers, I don't know, recurrent transformers, if you heard about them. So
Yeah.
I'm wondering, like, is this problem exists in them as well? Like, is it the same? Like, do they have the same problem? What do you think?
That they can't extrapolate to longer sequences?
Yeah, so basically something different will happen if we would just try them out on longer sequences.
Yeah, there's no current way to extrapolate to longer sequences than you've observed during. There's no model that does this at all. The best you can do is something like ALiBi, which lets you. So if you train ALiBi on 2,000 tokens, it can handle longer sequences, but it'll just start. So you train it on 2,000 tokens, and then you give it 4,000 tokens. It'll at token 3,000, it'll only look from between 1,000 to 3,000. At token 3,001, it'll look from 1,001 to 3,001. So it's only going to look at 2,000 tokens at each time step, and there is nothing that can do better than this. For example, as I said, the meta model that can handle 100,000 tokens was trained on 100,000. There is no current way to do true full extrapolation where you can train on a certain amount of tokens and then understand more at inference. It just doesn't exist right now.
I see, but at least I heard about some there are two works that came to my mind. The first one is the recurrent memory transformer. If I remember correctly, it's when we basically have like a hidden state in transformer and we pass it between like context windows. And the second one is block state transformer, where we essentially have some sort of RNN that precedes transformer layers. And this RNN is not just like LSTM or GRE, this is like a special like linear RNN that can theoretically handle very long context windows.
I haven't, the second paper that you mentioned, I haven't read it, but I do not think that they can extrapolate. And the first paper that you mentioned sounds very similar to Transform XL, which is ideas that we were playing around with like 3 years ago. And again, that can't really extrapolate to long sequences.
I see, thanks.
Yeah, we have a final question here. Are you aware of how ALiBi translates to vision transformers? Yeah, I tried it with vision transformers. It works, but people in vision don't really care about extrapolation to like longer images that much. Yeah, the same types of position embeddings that work in NLP also work in vision. But I think the vision community just isn't as interested in extrapolation right now, so they're not really looking into that stuff. Okay, let's go to the meat of the presentation. Yeah, so the final thing that I'll talk about before I talk about the directions that I'm excited about in NLP is this prompting paper that we wrote about this thing called SelfAsk Prompting. So this is a totally new topic. So if you lost us in this very technical, deep discussion of position embeddings, you can feel free to come in because this segment of my talk does not require any previous knowledge. Okay. So let's talk about the compositionality gap. So I think that the knowledge of a model is its ability to recite facts that it saw during training. And so to test the knowledge of a language model, we can just ask it questions about things that we believe it's seen many times during training. For example, what is the birth country of Plato? Or what is the calling code of Greece, right? That's pretty easy. But systems that are only capable of retrieving existing knowledge are very, very limited, right? If we're building the next version of Siri or Google search or whatever, of course, we want to answer questions that people have asked before, like how many feet are in a mile or whatever. But we also have to be able to answer novel questions that have never been seen before. And so in order to do that, I think we have to talk about the concept of reasoning. And for this talk, I'm going to define reasoning as the ability to combine two facts that a model has seen before in a way that it's never seen them combined before. And so we wanted to test the reasoning abilities of language models. And so we decided to do this by asking them these types of two-hop questions that we came up with So here's an example of one, and I'll talk more about it. What is the calling code of the birthplace of Plato? So we're asking it a question that combines two things it's seen before. What is the birthplace of Plato, right? It's seen that before. What is the calling code of Greece? It's seen that before. But we're asking it to combine it in a way that it's never seen before during training, right? And so I came up with these types of questions, and then I Googled a lot to try and figure out if anybody had ever asked these silly questions before. And to the extent of my search, I don't think anybody has asked these questions before. And so, yeah, so when we wrote this just before GPT-4 came out. So we're going to test GPT-3 here. And so we're giving it this one-shot prompt, and we're going to ask it what is the calling code of the birthplace of Plato, and it's going to say +30, which is correct. And when I wrote this paper, I was shocked because I've been doing language modeling research for 7 years. And when I first started working with language models, up until a few years ago, they were really, really, really bad. Like they couldn't even tell you, like, you know, stuff they'd seen a billion times during training, like, you know, where was Alan Turing born? And now not only can they tell you these things that they've seen during training, they can even do this type of reasoning. So that was just such a mind-blowing moment. But the thing is that, yeah, so wait, before I talk about this next thing, yeah, we made a data set of these questions. It's called Compositional Celebrities. All the questions are about celebrities because we know that the language model has seen facts about celebrities many times during training. And so there's questions there like who won the Nobel Prize in Literature the year Matt Damon was born, or what is the currency abbreviation in the birthplace of Kofi Annan. So we have 9,000 of these questions, but GPT doesn't always answer them correctly. So here we're going to ask it, who was the president of the United States when Billie Eilish was born? And it's going to say Barack Obama. And by the way, short interruption to tell you that I recently asked Claude 2 and LLaMA 2 these two questions. So if you ask them these questions and say, hey, LLaMA 2, please answer this question immediately. Do not think, like, just give me the answer. It'll answer it incorrectly. Like if you ask it to answer it right away. Claude 2 said Bill Clinton, and LLaMA said Barack Obama, and that's incorrect. So just like GPT-3 here, to correct, the right answer is George Bush. And now we're going back into the presentation. And so with GPT-3 here, you might think that it's answering this question incorrectly, either because it doesn't know when Billie Eilish was born, or it doesn't know who the president was on that date. And so we can just investigate that. We can ask it when was Billie Eilish born, and it gets that correct. So yeah, any text in green, that's something that GPT-3 has outputted. And then we can ask it, who was president of the US on December 18, 2001, and it says George W. Bush, which is correct. So we've discovered a reasoning bug in GPT-3. It is able to answer the two kind of simpler questions correct, but when you ask it this compositional question, it answers you incorrectly. Yeah, and we call that the compositionality gap. And in our paper, we empirically investigated this compositionality gap. And so what we did was, just like for the Billie Eilish question, we're going to ask it each of these 9,000 complex two-hop questions, like who was president of the United States when Billie Eilish was born. So that's going to be these blue markers here. And then, just like we did for Billie Eilish, we're going to decompose the compositional question into the two sub-questions that make up that question, right? So when was Billie Eilish born, and who was president of the United States at that time? And we're going to mark GPT-3 as correct only if it answers both sub-questions correctly. And that's going to be this green marker over here. Okay, so we're looking at the largest variant of GPT-3. It's 175 billion parameters. And it's able to roughly answer 60% of these question pairs correctly. So 60% means that it knows both that Billie Eilish was born December 18, 2001, and that the president of the United States was George Bush on that date, right? So for 60% of the questions, it can answer the two simple questions. But when we ask it the combined question, it only answers it correctly 30% of the time. So there's a gap here of questions, right, that it knows the answers to the two components, but it can't put it together. That's that reasoning bug, this gap. And the fraction of questions for which it happens is 41% in the largest variant of GPT-3. And the kind of shocking thing is that if you try the same experiment on the smaller variants, it's 40% basically all the way up. So it seems not to decrease as you increase size. So this is, an example of something that's not solved by training bigger models. We tested the compositionality gap for ChatGPT after the paper came out. That was also around 40%. With GPT-4, they've done something, we don't know what it was, but now the gap is 20%. So they've managed to decrease it. We don't know why. It might be a size thing. It might be training of different types of data. It might be because they have a different architecture, but they still have a gap even with GPT-4. And even I tried it with Claude 2. Like, all these models have this very, very interesting gap that's incredibly unhuman-like, right? There's no human in the world that could know when Billie Eilish was born and who the president was on that date, who wouldn't be able to answer that full question correctly. And this led us to create this SelfAsk method, which is, if you know about chain of thought, it's an improvement on chain of thought. So instead of just having a question and then immediately asking for the answer, we have this one-shot prompt with an example where we're like, okay, the question is, who was president of the United States when Justin Bieber was born? And then we're like, instead of answering right away, we're teaching the model to use this format. So first, the model is asking itself for follow-up questions needed here. It says yes. And you say who, follow-up, when was Justin Bieber born? Here's the date. Follow-up, who was president of the United States on March 1, 1994? Bill Clinton. So the final answer is Bill Clinton. So all of this I typed up, right? This is just the example prompt. And now we're going to feed it an inference time question. Who was president of the United States when Billie Eilish was born? This question that it failed to answer before. And it's going to automatically write, okay, I want to ask the first follow-up. When was Billie Eilish born? It answers correctly. And then it asks itself, who was president of the United States on December 18, 2001? It answers that, and then it says the final answer is George W. Bush. Yep. So that's SelfAsk Prompting. And yeah, it works really well. And it's able to totally close this compositionality gap, and it's able to have the model correctly answer any compositional complex question that the model has the information to answer. And the even cooler thing about this is that it enables easily combining language models with search engines. So that's the final system that we'll talk about. It's called SelfAsk plus Google Search. And here's why we thought it would be an interesting thing to build. So language models have limitations, right? They're very expensive to train. And so new ones come out very rarely. And so language models don't know about recent events. Or if you have your own data, internal data, or like, let's say you're doing something for like, you know, in the legal domain or in the certain scientific domain, a language model isn't going to have any access to that. And even if suddenly tomorrow, you know, GPUs become super cheap and energy becomes free, I don't know what, and we can train on all your private data and all your special data, it's still not going to solve the issue, because in the next 10 years, I'm pretty confident in saying that we're not going to have language models that are trained every second. And so language models are not going to know about real-time data, right? They're not going to know about the current stock price of Facebook or the weather in Japan. And so we have this other thing called search engines, which are really good at gathering data about recent events or about real-time data. But search engines, and I'll talk about this in a bit, search engines have a really, really hard time understanding compositional queries, right? So search engines are really good at retrieving singular, like, facts, like when was Barack Obama born, when was Billie Eilish born, who was president on December 18, 2001. But if you go and ask Google a compositional question, like go and ask Google, who was president of the United States when the 15th James Bond film came out, it's not very good at those types of questions. So we're going to combine search with language modeling to get the best of both worlds. Language models are really good at understanding complex queries, but don't have access to long tail data. And so, we're going to get the best of both worlds. So to show you the system, I'm just going to demonstrate how it answers the following question. So the question that I'm going to ask it is, what is the current time in the country that won the World Cup? So this is an IPython notebook, and it's on my GitHub. Just go to github.com/ofirplus/selfask. It's 50 lines of code. It's really simple, but here's what it's going to do. So we're asking it, what is the current time of the country that won the World Cup? And we have that same SelfAsk prompt that we were using before when we weren't interacting with Google. And so we're feeding this question to GPT-3, and it's going to ask a follow-up questions needed here. It's going to say yes. And we're going to continue just like we were before without a search engine. So it's going to ask the first follow-up question, what country won the World Cup? And now here comes the difference. We're going to detect that a follow-up question has been asked because it's very explicit here in the generated text that a follow-up question has been asked. And we're going to very simply parse out this question, which is very easy to do because you just parse out the text that comes after follow-up. And we're going to pause GPT, and we're going to send this question to Google. And then we're going to take the response that Google gives us. It's going to give us this long, like, this tournament has been held every 4 years. And we're going to kind of lie to the model. And we're going to tell it, hey, you just said this to yourself. Please continue generating. So we take the text from Google, and we append the words intermediate answer to this text from Google. And then we ask GPT to continue generating. So we're kind of lying to it and telling GPT that it told itself the tournament has been held every 4 years, blah, 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 even though Google just said this. But GPT-3 doesn't need to know this, or any GPT. And so GPT will say, okay, cool, I'm going to continue generating text. And now I want to say, what is the current time in Argentina? And so again, we are going to detect that a follow-up question has been asked. We're going to pause the language model generation. Again, we're going to take this question, parse it out, give it to Google. Google is going to give us a response. And then we're going to append the words intermediate answer to that response and feed this back into the language model. Then the language model is going to say, so the final answer is 11:12 p.m. And that's it. There you go. It's 50 lines of code. It's super simple. And this system is really, really, really powerful. It can answer many questions that Google and Siri don't answer. For example, this question is unanswerable by Google by itself or by Siri by itself, but this simple combination of Google and GPT solves it easily. And yeah, this is super exciting because it's the first approach ever for combining language modeling and search that doesn't require complex reinforcement learning, fine-tuning, or any extra training data at all, as in all these previous papers that have done language modeling and search. So it's really, really cool, and it's very easy to reproduce and extend. So yeah, it's on my GitHub, as I said. You can play around with the system. It's really fun. It might not be as powerful as Bing search or Perplexity, but it's very, very, very simple. It's super easy to extend, and yeah, I think it's really cool to play around with. So we show in the paper that SelfAsk does better than just asking a question and waiting for an answer across two existing datasets, and one dataset that we came up with called Bambooga, which we'll talk about in a second. SelfAsk also does better than chain of thought. So we show in the paper that chain of thought frequently loses its train of thought. It generates these really long explanations, and sometimes it forgets what it's trying to say, and it ends up saying something that's totally irrelevant. So with SelfAsk, the model is always kind of reminding itself what its current goal is. It's like, okay, the big question is, who was president of the United States when Billie Eilish was born? So it's like the first sub-question I want to ask is this. Okay, what's the answer? The second sub-question is this. What's the answer? So when models generate long sequences of text, they frequently lose track of what their goal is. So having this thing that focuses them after every line really helps performance. So yeah, I was surprised the chain of thought. The last thing I'll talk about here is that we came up with this data set called Bambooga. It's a question answering evaluation data set, and it's made up only of compositional questions that Google answers incorrectly. So we wanted to have a new data set of compositional questions, but we wanted to make sure that all of them were hard enough so that they were interesting for us to run an evaluation on. And so I came up with this idea of, okay, let's only find questions that Google screws up on. And so, yeah, I just sat in front of Google for 40 hours and I tried coming up with questions that would trick it. And a lot of the questions it did well on. But every once in a while, I would ask it a question like, who is the head of NASA during Apollo 11? And then it says Eugene Kranz, which is incorrect. You can even see it right here. It said that he served as the chief flight director for Apollo 11. I asked who the head of NASA was. So this is an incorrect answer. So when I found something like that, I would put it in the data set And so, yeah, it's really cool that this system, I think that we get 70% accuracy with our SelfAsk and GPT and Google approach, whereas Google, as I said, gets 0% accuracy. So it's really cool that 50 lines of code that combine language modeling and search can do so much better than Google search on these types of tough questions. Yeah, I said that was incorrect. And yeah, I've been told that Bamboo goes used internally at Google to evaluate search and language modeling, which is really cool. Yeah, we have some time for questions, and then I can talk about future work. So we have one question from Trevor. Would it answer the George Bush question correctly if asking the reverse order? Yeah, of course. If you break down a question, it makes the you're basically doing the decomposition for it, and so it would answer that correctly. And so the entire idea with chain of thought and SelfAsk is not to, it's just to show that language models have a really, really tough time answering compositional or complex queries, and that the way to get them to do it is to get them to first break it down into subpieces, tackle each one of the subpieces by itself, and then give you a final answer. So that's what chain of thought does, and SelfAsk is simply an improvement over chain of thought that does it better by always specifying what sub goal we're working towards right now. So yes, we have another question here. Oh yeah. So this question was asked when I was talking about the Billie Eilish stuff, and this person says that these questions don't seem realistic. They are not realistic at all. They are just questions that we kind of generated to kind of have like this large data set of questions that we could benchmark these systems on and figure out what their compositionality gap is. But yeah, these questions aren't super realistic, and so that's why we created Bamboogle, which does have much more realistic questions. But the results were quite similar, with SelfAsk being really good and better than chain of thought. Yeah. We have a question from Anna. How does ChatGPT choose to answer composite questions? Yeah, so these models are being trained with chain of thought. So Claude and LLaMA 2 are really, really good at understanding that when they have a tough compositional task ahead of them, like a compositional question, they should try to break it down into sub-questions first. So these models are getting better and better at doing these things. But all this stuff that I talked about is still super important to understand, because sometimes these models fail to understand that they are standing in front of a compositional query that they must decompose, and they try to approach a compositional task without decomposing it first, and then they end up returning incorrect results. So the takeaway message from this is that language models are not very smart. They are not good at doing things which they did not see during training. They are not good at solving compositional tasks. And so when you prompt language models, I urge you to look at chain of thought, to look at SelfAsk, to write a prompt that encourages the model and shows it how to decompose whatever task you have for it into simpler subtasks, solve those, and then solve the main task. That's the takeaway message.
Before we go to next question, if you want to answer further, like maybe we could invite some people to ask their question out loud if they want.
Sure, Kartik can ask.
Yeah, if people want to ask the questions out loud, please just raise your hand and I'll unmute you. Yeah.
Oh, Anna has a follow-up question.
Yeah.
Sorry, can you hear me?
Yeah.
Yeah.
Hi. Sorry, I just had a follow-up question. Why did it answer Barack Obama in that question? How did it choose the answer? I'm not quite sure.
Oh, well, we don't really know. We don't know how language models work internally, right? We just ask it a question. And if we're using chain of thought or SelfAsk, then we can see kind of its reasoning, logical chain. But when we're doing what's called direct prompting, where we're asking for the answer right away, it just says what it says. And we don't really know how language models work good enough to be able to tell you why it chose that specific answer. But Language models are kind of always trying to approximate things. So it's Billie Eilish. It needed to give an answer straight away. So it was like, Barack Obama is in the vicinity of the synthetic space, but we don't really know how language models work. So we don't know why it chose Barack Obama. I mean, this is a tough question. It wasn't trained on these types of questions. So yeah, it just doesn't do really well. And that's why it's really important to decompose complex tasks into simpler subtasks, because those are simpler to what it saw during, those are more similar to what it saw during training, or if not equivalent to what it saw during training, and then it can tackle them.
Thank you.
There is another question that was mistakenly sent to chat instead of Q&A section. Oh yeah, it was addressed. Yeah, so Aaron, if you want to ask your question out loud, you can do that.
Does Kartik want to ask his question? I can actually answer it. Is this so no, the early token curse, late token curse. Oh, that's an interesting question. So Kartik asks, is there a late token curse here too, where the usefulness of the generated text falls off the more text the model generates? Yeah, that's a very interesting research question. We definitely know that models can't really extrapolate. So if you train it on 2000 and you try to get it to generate more than 2000 tokens, all the tokens beyond 2000 are not going to be very high quality. They're probably going to be incorrect. And so there definitely is a late token curse there. But even when we've trained GPT-4 on 8,000 tokens, it's pretty common. I'm sure you've seen this too, that when you ask it to generate long text, the longer the text is, the less accurate it becomes sometimes, right? We show this example in the paper where we're using chain of thought, and the question that we're asking is, who was president of the United States when superconductivity was discovered? And we're using chain of thought here. And it says superconductivity was discovered in 1905, which is correct. And then it says the president of the United States in 1913 was Woodrow Wilson. So the final answer is Woodrow Wilson. That's obviously incorrect. So that frequently happens with chain of thought, where it's just generating this long, undemarcated bunch of text, and it loses track of what it wants to do. And so, yes, so getting it to kind of generate things in smaller chunks is definitely very helpful. And that's why SelfAsk is so useful, because instead of presenting the model with this large, complex task, it's like, forget about the large, complex task. First, just decompose it into simpler subtasks, and then answer the first subtask, the first sub-question, and then the second sub-question, and so on. So yeah, that's that. We have another question in your examples for SelfAsk. So yeah, I don't really understand Elio's question, but
actually I had a similar question. Maybe
yeah,
I could phrase it.
Yeah.
Like so what if, so basically SelfAsk works well, or like without Google or with Google.
Yeah.
Like we assume basically that it knows which atomic question to ask. But what it doesn't know, and what if it's like simply not possible to ask such question, or like it needs to have some knowledge, or like it is simply impossible to ask it. But like, is there like a gap that remains in SelfAsk that could be attributed to this inability to ask the right question? And like, what should we do with this like unanswerable atomic questions?
Yeah, that's a really good question. So we had a very hard time finding questions which SelfAsk could not decompose. Just for fun, we started asking like 3-hop questions and 4-hop questions, which are questions that require 4 pieces of evidence or 3 pieces of evidence. And SelfAsk basically almost always decomposes them. We did find 1 or 2 cases where it did something incorrectly. Like one of the questions in Bambuga is, how much protein is there in 4 boiled egg yolks? And that's a question that Google can't answer. Or couldn't at the time. And what I wanted it to do was to break it into how much protein is there in a boiled egg yolk, and then what's that times 4. And it didn't do that correctly. But other than that, I basically can't think of any examples. So yes, it does happen, but it's very, very, very rare. And a matter of fact is that most questions that users ask are a single hop. And when they ask the 2-hop questions, they're not super complex. So we haven't noticed that being an issue in question answering. There's one more question from Arnon. Should we do that?
Yeah, let's just answer this final
Okay.
question before we wrap up.
Yeah, so Arnon is asking if we tried asking adversarial questions, meaning questions with no right answer. And actually, it's a super interesting question because this whole thing started by me trying to troll ChatGPT and ask it questions that have no right answer, like which Canadian shot JFK, when did Spain land on the moon? And then after I started playing with this, I saw that people on Twitter were also doing these types of things. So somebody on Twitter asked it, when was the Golden Gate Bridge moved across Egypt for the second time? And at the time, if you asked GPT these absurd questions, it would give you dates. So like, when did Spain acquire nuclear weapons? So it would be like, probably the 90s. I don't know. It would say like, December 1, 1992. And it's happening because when this model was trained, whenever somebody would ask a question, there would be an answer there, right? When humans are asking questions on the web, these questions are usually correct. And these questions are usually answered. It's not very frequent to have a Stack Overflow or a Reddit question where the answer is, hey, like, you're totally wrong. Like, what the hell? Like, there's no answer here. And so the distribution that this model is trained on is like, when it sees a question, it has to supply an answer. And when it sees a question that's like, that starts with the word when, it should supply an answer that is a date. And so ChatGPT kind of followed this reasoning that it was trained with, and it would just supply these absurd dates. It seemed like an issue at the time, but I discovered a very simple way to solve this, and I prompted it to do the following thing whenever a question was asked. Just first, I had it think about whether the question was valid. So I had this prompt, right, where the question was, which Canadian shot JFK? And then the second step was, is this question valid? ? And then I would write like, no Canadian has shot JFK. And then I would write answer, no answer. And then that was the prompt. And I would ask like, when did Spain develop nuclear weapons? And then ChatGPT would correctly say Spain never developed nuclear weapons, therefore there is no answer. And so you can ask ChatGPT these absurd like adversarial questions. If you don't prompt it well, it will give you silly answers. But it's an issue that is very, very easy to solve. You just give it a few of these silly questions in your prompt. You show it that it can reject. It can decide not to answer these questions, and then it does it really, really well at inference. Yeah.
Okay. Unfortunately, we ran out of time, but I would like to thank Ofir and Artem again for the very interesting talk, where we learned a lot about the limitations of the latest large language models. And thank you all for attending the meetup. Just a reminder that the talk is going to be published on our YouTube channel, so look for the London Machine Learning Meetup channel. And also stay tuned on your email, because we're going to have some in-person events. So we'll send a few notifications in the next couple of weeks. Right. Thanks again, guys. Very nice meeting you.
Thank
See you at
you.
the next meetup. Bye-bye.
Bye.